So talk about a project that's been going on for about 4 years and various things. The idea is to try to get roughly bare metal performance, even though we've got the entire Linux kernel at our fingertips as an application, and as it says, now with added energy efficiency. This has been a large number of people doing a lot of work over a long period of time. I'm not going to go through these all in detail, but Frederick Weisbecker is worth special mention. He's done a lot of the heavy lifting in getting the core code and also the x86-64 port going. So a lot of this is his work. You know, there used to be some things you could count on. Some things you still can count on. But one of the things you used to be able to count on was a scheduling clock interrupt every jiffy on every CPU. Very reassuring rhythm, always there for you. And we needed that because if you had multiple CPU-bound applications, CPU-bound tasks on the same CPU, you needed some way to make sure that you wouldn't have monopolization of CPU, that you wouldn't starve the extra tasks. And so we got the operating system interrupting the CPU every so often and making sure that it's doing the thing that's most important at that point in time. But one of the side effects of that is you got that whether you needed it or not. And in particular, you've got this poor guy, he's only got one thing to do, and he's getting interrupted every jiffy. And it's disrupting him, it's messing up his cache, and it's taking up time and causing trouble for no good reason. And of course, once we get to battery-powered systems, we have the question of whether your battery needs this or not. And you can imagine this poor battery getting beaten up by this clock happening fairly often, and it's just, The battery-powered embedded guys get really excited about this sort of thing, and it's not in a good way. I've gotten very nasty phone calls from people when they felt that RCU was doing too many scheduling clock interrupts and decreasing their battery lifetime. They were claiming like 10 or 20%, which surprised me, but that's what they said. Anyway, regardless, we don't want this, okay? This is not the way we want Linux to behave, especially on small battery-powered platforms. Of course, back in the old days, you needed a somewhat larger battery for the system. And in fact, if the system was portable back in the old days, you needed a forklift to move it around. What we really want is something like this. We want, if there's nothing happening, we want the clock and the battery to see asleep, be peaceful, not waste energy, and life to be good. And that's what this work is about, trying to make bare metal work that way. So in the old days, this is kind of a diagrammatic thing. We've got two CPUs, time going from left to right. And the vertical red bars are scheduling clock interrupts. And if the CPUs are busy, like they both are initially, the red color, then we go along, we get our scheduling clock interrupts. Then the yellow part, they're both going idle, but they're still getting scheduling clock interrupts. Now, back in the 90s, this was actually optimal because the highest energy dissipation for a CPU was when the idle loop. And the reason for that was that you had no cache misses, the ALU was going full bore, just going around this little loop. And that was, your worst case. In fact, there were some high-speed CPUs that if you left them idle too long, you'd have problems where the clock would, fracture the chip because of the heat dissipation. So you have to replace your CPUs every few years. But these days, things are much more sophisticated. And the CPUs, when they're idle, are much more aggressive about shutting themselves down and consuming less power. And the scheduling clock interrupts are disrupting that. Depending on how quickly the CPU can decrease its power consumption. Some of them can do it quite quickly, but you still have the consumption of the scheduling clock interrupt itself. And for some CPUs, the fact that the scheduling clock interrupt happens means that for some period after that, or some period before that, you still have increased energy dissipation. And that's why, you think about it, I wouldn't be too happy if somebody did that to me. I'm trying to sleep, and every jiffy they're whacking me and waking me up. I wouldn't take too kindly to that, and the batteries don't take too kindly to it either. So this is what we have for idle now. We've had this for almost a decade with the Dynatic idle system. And what happens is that when a CPU goes idle, it shuts off the scheduling clock interrupt, at least assuming you have config no hertz equals y, which I think is the default for most distros these days. And that's nice because it means the CPU can go down to the lowest energy state possible and conserve energy and increase battery lifetime if you're a battery-powered system. Even if you're not a battery-powered system, conserving energy is not a bad thing. Okay, that's wonderful, but the thing is that there are some applications HPC, which is high performance computing, where you have these massive numerical applications that tie up machines for weeks on end. And real-time applications can actually increase performance. In the real-time case, that'd be decreasing latency, if you can get rid of scheduling clock interrupts while they're running in user mode. And the thing is that the reason we have the original textbook reason for a scheduling clock interrupt is that we need to be able to avoid starving applications, so there's multiple runnable applications on a given CPU. But if we've only got one runnable task on a given CPU, we're not helping anything by interrupting it. In fact, we're slowing it down. And for both HPC and real time, that's just not helpful at all. We're increasing our latencies, scheduling latency, interrupt latencies in the case of real time, and we're introducing OS jitter that slows down iterations in the HPC case. Now, the idea would be is if another task shows up, at that point, we'll deliver an interrupt to the CPU. Perhaps it was an interrupt that was delivered directly to the CPU from a device, waking it up, and then it does a wake up, and now we can start the scheduling clock interrupt if we need to. Or perhaps it was a wake up from some other CPU, in which case there's an inter-processor interrupt that will wake up that CPU, allow it to reevaluate its situation, and say, oh, okay, there's actually two tasks now, therefore I need a scheduling clock interrupt. But as long as you only have one runnable task per CPU, interrupting it really isn't helping you. And so we got this poor CPU again being interrupted. It's only got one thing to do. We're slowing it down. We're messing up its cache state. We're not helping anything. Okay, so Josh Triplett, was an intern back then, a real smart guy, and he did a prototyped. He didn't call it this. It was just a patch that did this. And what it did was it unconditionally turned off the scheduling clock interrupt for any CPU running in user mode. Just as a prototype. There's some obvious disadvantages to doing that we'll get to in a slide or two. And Anton Blanchard ran some tests on this. And without that patch, just using scheduling clock interrupts in user mode as normal, you get this kind of a thing. And this red area is a slowdown. In other words, the application was being slowed down by between 3 and 4% because of the scheduling clock interrupts, which is not a huge difference, but the HPC guys will do quite a bit for a few percent. Yeah. As Dave said, yes, they'll kill for that. I was thinking in terms of selling their grandmothers, but okay, I'll bow to your greater expertise. When he applied Josh's patch and reran, he ended up with that. Same vertical scale, and there's just a lot less of that red, and so things are going much faster. Now again, as I said earlier, Josh's patch was strictly a prototype, and it had a few disadvantages. One of them was that it was plenty happy to let a given CPU-bound user application monopolize the CPU regardless of whoever else might need it at that time, which was a problem. But again, as we said before, if you only got one runnable task on that CPU, who cares? I mean, at that point, you want it to monopolize the CPU. The CPU doesn't have anything else to do. And again, if a new task awakens, we can interrupt it and get it to change what it's doing and go from there. Another problem was there was no process accounting, which is less of an issue than it was back in the time-sharing days where they were charging for CPU time, but still, there are some places where you have monitoring tools and other sorts of things that really care about what the CPUs are doing. And a way in theory, this is really simple to deal with. You use delta-based accounting. So when this task started, you record the time and record the fact that there's tasks there. When you want to find out what the CPU is doing, you say, okay, well, how long is the instance then, and add user mode up to that point, and away you go. The reality is somewhat more complicated, and if you want the details, ask Frederick. He had to fight that one. Another thing that you have is timekeeping, and we'll be talking about that later in this presentation. You have to have one CPU retain the scheduled clock interrupt for timekeeping purposes. The one that involved me the most was the fact that if you do this, RCU grace periods go on forever. And that means that when the system wants to free up memory that's been available to RCU readers, it just can't until this guy comes into the kernel. And at that point, you eventually run out of memory, which can be bad for your availability. So as I said earlier, Frederick took on the task of fixing this for x86-64. Jeff and Kevin ported it to ARM. Li Jung ported PowerPC, and I did a little bit of RCU work for it. So, how well does it work? The top is beforehand. During idle, the green part there on the top, We don't have scheduling clock interrupts, but as long as we're in kernel or user mode, we do. With adaptive ticks, we get rid of them entirely until such time as a second task awakens, shown on the far right there. And this, again, assumes we have one task per CPU initially. So that works out pretty well. But as always, in the first round of things, there were some drawbacks. And one of the things is that the battery-powered guys weren't very happy with us. They were upset about energy efficiency when they enabled no hertz full. Now, it's not clear to me why they're running real-time or HPC applications on a battery-powered platform, but presumably had some reason for enabling it. And, well, energy efficiency is becoming more of a concern, so it seemed worth worrying about it in any case. So why did we have to have those extra scheduling clock interrupts? The reason they were upset is that the patch, or the stuff in the main line right now, if you enable this, it will keep the scheduling clock interrupt on CPU 0 on unconditionally, regardless of what's happening with CPU 0. All right? And the reason it does that is because hardware oscillators drift, and if you have an application that really cares about what the time is to fine detail, and there are some that do, then you have to periodically recalculate offsets and multipliers and things like that, NTP being an example of that. And if you don't do that for long enough, the user applications are going to get bad time data and eventually have some applications going to have failures because of that. However, there is one special case where we don't need to do this at all, and that's if all the CPUs are idle. If all the CPUs are idle, then none of them care about timekeeping. The idle loop, one of the constraints in the idle loop is you're not allowed to pay close attention to the time because it's not being really updated very well. And at that point, what you do is when the first CPU realizes it's gone non-idle, it recalculates the parameters at that point to ensure that by the time user code is executing, it has access to accurate time. So in diagram form, we have something like this. It's kind of like before. The capital T's there are we're doing timekeeping, so we're doing it at each scheduling clock interrupt on CPU 0, and we're also doing it when CPU 0 goes non-idle, because it hasn't happened for a while, and therefore we need to do it again. And the thing is, in that green area, between the two dotted lines, there's no need to do parameter recalculation. Nobody cares about the time if everything's idle, so we can just let it drift, and then when we come back on, when CPU 0 goes non-idle again, we'll recalculate it, catch things up, and life will be good for the user mode execution after that. But if we're running user space without a scheduling clock interrupt, we have to worry about time. So if we have that same diagram we had a couple slides ago, but CPU 1, instead of being idle, is running the user, we have to keep the time accurate during that time. Now, we want the user not to get scheduling clock interrupts, but we want the time to be accurate as well. And we have to do something to make that work. If we did it this way, it would break. So the thing is that what we want to do is we'd like to be able to tell if any CPU is non-idle. If there's any CPU non-idle, we have to be updating the timekeeping. We have to have scheduling clock interrupt somewhere. And again, the initial approach we chose would just say CPU 0 is going to do this all the time. And the reason that sort of makes sense, at least if you're not battery powered, is that the HPC and real-time guys normally reserve some CPUs for housekeeping purposes. So and often CPU 0 is a good place to put it because it's the boot CPU and often gets extra chores anyway. And so they'll have one or more CPUs whose only job is to sit there and take care of background housekeeping stuff, and the rest of the CPUs are what runs the actual application. And so if we use that approach and have CPUs there, the fact that CPU 0 is running the scheduling clock interrupt all the time isn't really hurting the application. But if everything's idle, it is hurting energy efficiency. But so what happens now in mainline is this. CPU 0 always takes a scheduling clock interrupt whether it's idle or not, and if some other CPU goes in user mode for a long time, it can rely on the fact that CPU 0 is doing the scheduling clock interrupt to keep time accurate. Yes?
So is the scheduler by default biasing so that it assigns jobs to all CPUs and 0 by first and then back 0 and then it's full?
So the question is, does the scheduler bias things to assign jobs to some other CPU? And there is some bias of that sort. If you have a CPU-bound job and CPU 0 happens to be busy, it'll have a higher probability of being busy, so you might put it elsewhere. But if But oftentimes, the housekeeping CPUs are not very heavily utilized, and so that won't be very strong. Usually what people do when they're running these kind of workloads is they force the tasks on the CPU they want them on. And one of the downsides of this whole approach is that it takes a fair amount of work to get the working CPUs to be really clean. And we'll get into that a little bit later. But yeah, there's some tendency for the scheduler to push stuff off of the housekeeping CPUs, but it's not a very strong tendency. So in reality, you have to do something, C groups or affinity, sched set affinity or something, to actually force the work to go where you want it to.
Would it be possible to do the timekeeping, the housekeeping in the moment when the user process requests the time instead? For example, by system call.
Okay.
Okay,
so the question was, why can't we just ignore the time, let the time drift until such time as the user process does a timekeeping system call, get time of day or get clock or something like that? We could in theory, but there's a number of architectures that use VDSO so that the kernel isn't aware that they're doing a time call, that they're getting the time. It's just a library function that goes and grabs some stuff in some pages that are mapped out of kernel memory, and the kernel has no idea it happened. Now we could say, well fine, if you really want this, just really do the system call. Okay, so configure your kernel so that it really, there's no VDSO and it really is a system call. And you could do that, but that slows down the timekeeping, and there are some applications that are in this mode that really want the time very, very often if they're doing input data and having to correlate with time or something like that. So it's a good approach, but given the way things work in the kernel now and the time and what some applications need, it wasn't something that did everything we needed for everybody. Okay. All right. So that's what we do now. It sort of works. It doesn't make the battery-powered guys at all happy. In fact, anything but. They're not too happy about it. It was kind of an education for me when I went to Lenaro for a few years a bit ago. I felt as a server guy, I also have a mechanical engineering degree, so I understand energy and energy efficiency, right? The thing is that us guys in the server area might have energy efficiency as a hard requirement. But as near as I can tell, the battery-powered embedded guys have it not merely as a hard requirement, but rather as a fundamentalist religion. Okay, and if you do something that messes up their energy efficiency, they will react accordingly. So you want to kind of be sensitive to it. So what that means is if the system is idle, we really want to shut down all of the clocks. We really want a better solution. What we have works for a good subset of the population. It works for the people that have servers and want to do HPC in real time. It's not something that works for the battery powered, and so we'd like to do a little bit of work to fix that hole. There's a couple really simple but totally broken ways of dealing with this. And one of them, just count, right? What could be simpler? Have an atomic variable and use atomically increment when somebody goes non-idle. You atomically decrement when they go idle, and there's your number. If it's 0, you turn off all the schedule clock interrupts. What could be simpler, right? Dave Chinner might have a few words from his SGI background on how well that works on large systems.
You can deadlock the machine with cache coherency protocol.
So he says you could deadlock the machine with the cache coherence protocol. I'm not sure if that's a bad thing, but he seems a little bit upset by it.
When you're doing it for just an atomic count.
So apparently the people who run big machines don't like this approach very well at all. And I used to run machines large enough I never deadlocked the machine on the cache coherence protocol, but we certainly at Sequent had machines large enough that it just was taking the machine and making it totally non-scalable. So it's a really bad idea with systems with lots of CPUs, not what you want to do. So another approach is to be a little more leisurely about it and just scan all the CPUs looking for the non-idle ones. Just go through the list and take your time and get through there, and if they're all idle, right? Unfortunately, this is vulnerable to some race conditions. So let's suppose we have 4 CPUs. So the timekeeping CPU looks at the CPU 0 and says, oh, it's idle. Great. Okay, 1 CPU is idle. And then after that, CPU 1 goes idle and CPU 0 goes non-idle. So at this point, we have 3 CPUs non-idle and 1 of them idle. It looks at CPU 1 and, hey, it's idle too. And I think you can kind of get an idea of where this is going. So at the end of the scan, it's seen, every CPU it's looked at, when it looked at it, was idle, but there's never been fewer than 2 non-idle CPUs the whole time. And so it gets to the end and says, oh, everybody's idle, and shuts down the scheduling clock interrupt, and people get lousy time after a while. So this doesn't work either. And the thing is, we're going to have to give up something. Well, if we try to give up energy efficiency, the battery power embedded guys are going to be bringing their crosses, crossbows, crescents, and lighted torches after us, so that's probably not the best approach. Scalability, Dave Chinner is going to be upset at us, and probably a lot of other people too. Determinism, well, the real-time guys aren't going to like that. Anyway, yeah, we heard some commentary on the other ones. So let's see what we got here. Let's take a look at a large system and see what happens. I mean, what you'd like to do is if you had a workload that had a certain amount of utilization, you'd like to opportunistically identify the idle periods, the periods where the whole system was idle. And then at that time, turn off the scheduling clock globally. So a reasonable question is, what's the probability of the whole system being idle given a certain utilization and given a certain number of CPUs? And that's what this chart does. Notice this log scale in both directions. So, so here we have the percent of time in full system idle, and that's a percent. So probability 1 at the top and a very low probability, 10 to the minus 6th at the bottom. All right? And we have number of CPUs across the x-axis. And these traces, each of them has a different utilization. So if the system is 90% utilized, life gets very hard very fast. The system is never all idle, or the probability of it all being idle is really, really low. And so it's almost never all idle. Why worry? Let's suppose we're doing 1,000 CPUs.
Where can I buy this system? Where could I buy this system?
The one with 1,000 CPUs? Yeah, talk to the gentleman. The question was working by such a CPU, and the answer is talk to the gentleman sitting next to you. I'm sure he'd be willing to sell you several of them. I would be too, for that matter, but he's sitting next to you, so he's more convenient. Dave's old employer would probably be happy to do so as well. Okay, so at 1,000 CPUs, even if we have a 1% load, we've got like a 10 to the minus 5th chance of the whole system being idle. And the only time we have a chance is at about 0.1% load. In other words, out of the 1,000 CPUs, 10 of them are in use at any given time. And at that point, we're running at about, 10% or maybe 20% chance of the whole system being idle. But I would suggest that if you have a system that has 1,000 CPUs and its utilization is 0.1%, I mean, I'd love to sell you 1,000. My employer would love to sell you 1,000 CPU system for that situation, but I suspect that you might be better served by a somewhat smaller system. From a technical standpoint, of course. So what it comes down to is, for large CPUs, forget it. This just isn't going to buy you anything. The opportunistic idle with these kinds of probabilities for a large system, it's not going to be idle if you're using the system at all efficiently. So what that means is that if we have a large system, the only time the whole thing goes idle is if the workload is shut down for some reason. All right? So maybe we had a big batch job running, and it shuts down, and we have to get ready for the next one, so the system's idle for a few minutes, and then we start the next one up. Or maybe it's a holiday and there's just nothing for it to do. Although with a big expensive system like that, there's probably never a time when there's nothing for it to do, but we can suspend disbelief. But the thing is the time when it's all going to be idle is when there's nothing for it to do and it's really just there, and that's probably going to extend for some period of time. So what that means is that what we can do is for the larger machines, just take longer to recognize that the full system is idle. And the advantage is if we artificially extend the latency, we can keep the memory contention on that variable down to an acceptable level. And so what we're going to do is that latency is going to increase the more CPUs we have. And of course, on the last one, you guys might have been laughing about that on the last slide. Of course, in my case, you can't give up something you never had. So that just wasn't an option. So, Okay, so what we're going to do is we're going to give up latency, and if we have a large system, we're going to take longer to figure out the thing's idle, and we're going to have some unnecessary scheduling clock interrupts for a little while, but after a bit, we're going to recognize it and shut everything down. And of course, we'll use a state machine. What else would you do? Of course, being who I am, one possibility that presented itself fairly quickly was that RCU happens to scan idle CPUs already anyway. The reason it does that, if a CPU is idle, RCU has to ignore it. But it can't ignore it by asking it. I mean, the whole point of letting it be idle and not doing anything with it is for it to just not do anything. So RCU can't expect that CPU to do anything for it. So it has to scan data structures for each CPU that hasn't responded to say, all right, is this thing idle? And of course, if it has responded, then it's not idle, clearly, or wasn't recently. All right, so what we're going to do is we're just going to take that pre-existing scan and add a little more work to it. And the main thing we're going to do is we're going to keep track of the last time a CPU went idle. Okay, and the reason for that is that we don't want to turn off the scheduling clock interrupt on a large system unless it's been idle for some period of time. So we're going to go through there, we're going to keep track of who's idle. If they're all idle, we're going to have kept track of the one that most recently went idle, and that'll give us how long it's been there. When that time gets up to a long enough point, we'll say, okay, great, now it's time to make the transition. Of course, that begs the question of how long we should do that, and also, well, let's talk about the state machine first. I'm not going to go through this. This is for people that are reading it afterwards. We're going to use the diagram to go through this. Same information, different format. So we have 5 states going across, and over time we'll advance from left to right as the idleness continues for a longer period of time. And if somebody shows up non-idle in one of the later states, we'll go back to where we started. So we start in RCU sys idle not. In other words, there's somebody non-idle or we've just started. And if we do a scan and find that everybody's idle, now that scan may have been fooled. We're not doing anything special. That scenario I had showed up before where the CPU was only idle when we looked at it and went non-idle immediately afterwards. That could happen. So we get to this state and have people non-idle. But that's okay because we've kept track of the time. And so if they've been doing that, we'll go through there and see they've only been idle for a short period of time. And we transition to this state only if not only are all the CPUs idle, but they've been idle for a long time. All right? And at this state, if somebody shows up and they see that we're in this state and they're not idle, they say, well, whatever, ignore it. Okay? And that means, because if we did otherwise, we'd be changing this variable frequently, and that would give us memory contention. Instead, we wait either for long enough for everybody to go idle, and if we never have that state, yes, Ben?
Can you define long time?
Can I define long time? Yeah. Sorry, I couldn't resist. Not that I ever try very hard. I've got a slide later that shows exactly what long time means right now, although whether that's the right definition or not is an interesting question I don't know the answer to yet.
My worry, basically, you're always going to have some kind of something in use baked in. Just going to break one of them up a little bit, just enough that we may monitor the.
Yep. Yeah, and that's a problem. If you have an application, so what Ben said is he's worried that there might be some user mode application that just has this daemon that wakes up unnecessarily and keeps this forever happening. And so one thing that I've forgot to mention is that this is only looking at the non-timekeeping CPUs. There can be everything in the world happening on a timekeeping CPU, and it'll ignore that. It'll just be going up through the state still. It only looks at the non-timekeeping CPUs for this determination. And the reason for that is that it's a timekeeping CPU that's going to turn off its clock. Furthermore, somebody has to execute the state machine. And if we required everybody idle, then we couldn't, every time we do a scan, we'd kick ourselves back. Yes, I learned that the hard way. What can I say? And we'll get to how long is. But the idea then would be that to make this work, again, we're an HPC or a real-time application, you want to take all of your non-work stuff and confine it to the CPU 0. Or some small number of CPUs. And the load on those CPUs is ignored for this purpose. And so hopefully you've got the user mode applications putting all their stuff there, which they probably need some help doing, but and then at that point they don't disrupt the idleness. Okay, so if they've been idle for long enough, whatever that means, At that point, we move into this RC sysidle long state. Now, again, somebody could go non-idle immediately, but that's okay because we're going to do one more scan over here. And in addition, if somebody goes non-idle, we now transition back to the base state. The reason we're willing to do this here is because it's taken us some time to go through these states. And we're adjusting that time, making that time longer for more CPUs, which means that the memory contention on that state variable remains bounded no matter how many CPUs you have. All right? And then once we get to this state where it's fully idle and it's been idle for another scan, at that point, if the timekeeping CPU asks us, hey, are you idle? We say, yes, we are right now. We update to the noted state saying we have been fully idle and we've told the timekeeping CPU about it. And what that means is that if somebody goes non-idle, we don't just transition to the state, we also wake up the timekeeping K-thread and say, hey, somebody's non-idle, wake up, do whatever you need to turn the scheduling clock interrupts back on and go from there. So a fairly simple, straightforward state machine. The basic trick here is to make sure that the state changes happen slowly enough that the large machine's cache coherence protocols can keep up. Okay, so to Ben's question, how long do we stay in the RC sysidle short state? How long is long enough? So again, a CPU going idle records the time, and that's what we use to do the calculation. And when RC does a scan, it remembers the most recent time, the shortest time of a CPU being idle. And we only advance if it's been long enough. And the long enough increases linearly with the number of CPUs. And we also adjust that by hertz. If you're running at 100 hertz, we're going to go 10 times as fast in terms of jiffies than if you're going 1,000 hertz. We also adjust by the number of CPUs per RCU node structure because that's kind of a funny measure of how difficult if you have a default of 16, you're saying, okay, I've got a fairly fast interconnect. If you've set it to 64, and if you have pushed it up to 64, then you're making a statement about believing you can handle lock contention more. And I'm kind of using that as a proxy since I don't have any way to directly measure it really. Or maybe I do and don't know about one. If there is, let me know. And so I use that as a hint. So that's how long enough is, at least with the current parameters, and maybe this has to change. So if you have a 4096 CPU system, it takes a little bit over a quarter of a second, 250 milliseconds, to make the transition once the whole system goes idle, which should be reasonable. I think if you're having, go ahead.
If you've got 4,000 CPUs, then that's more than reasonable.
I'll take that. Dave's thing is if I got 4096 CPUs, that's more than reasonable. I'll take that as a vote of confidence. So that's the current thing. Maybe it has to change. Maybe it needs more parameters, but that's what we're doing right now. Start something fairly simple. Of course, I described the state machine. There's a number of races that might happen. And the bad one is if the timekeeping CPU turns off all the scheduling clock interrupts and fails to notice a CPU going non-idle. That would be bad. And this just kind of gives an informal reasoning of why this doesn't happen with this algorithm. So the idea is that if the CPU goes non-idle and we're in the RCU sysidle full noted state, okay, if a CPU goes non-idle and it sees that we're in this state where we've told the timekeeping K thread, hey, shut off the interrupts, then it'll see that and it'll wake up the timekeeping thread to turn them back on. And if a CPU goes non-idle in any state, except for the short state and the not state, it's going to force it back to the not state. And what that means is that any time we first decided, hey, it's been idle long enough, there's at least one more scan. And while we're doing that scan, we're in a state where a CPU waking up, going non-idle, will force us back into another state. All right? This does require careful use of atomic operations and memory barriers, and getting it right is a little bit harder than it looked, at least to me initially. So looking at what we do with that, again, repeating if any CPU can drive state, any CPU can drive back to RC sysidle not. But what happens is when that happens, when it says, okay, I'm going non-idle, and the state is far enough along, there's a risk of shutting off scheduling clock interrupts, what it does is use an atomic exchange instruction to set the state back to the base state. That means it gets back what the state really was, okay? If it sees that the state it got back was this full noted, it says, oh, well, okay, in this case, the K thread has already shut off the interrupts, or it might be about to, and so we need to wake it up and tell it, look, start over and turn things back on. One restriction right now, I may have to change this. Frederick and I are kind of negotiating. He's doing the stuff to integrate this into no hertz full, is that only one task is permitted to advance the state. And if you have a very small number of CPUs, it's the timekeeping K thread itself. If you have a larger number of CPUs, it's the RCU grace period K thread. Though there's a particular one that is the one that drives the state, and it's that particular one. And what it does, when it wants to update the state, it uses compare and swap, compare and exchange. And it only tries it once, because the only reason it can fail is if somebody said, ooh, we need to set the state back. So it tries. If it succeeds, great, the state is advanced. If it fails, that means somebody else put it back to naught, and we just say, okay, we're done, get out. Of course, it's quite possible that a CPU might, going non-idle, says, oh, it's only been a little bit of time, I don't have to mess with the state, but then immediately after that, the state goes to long. But that's okay, because there's memory barriers in the right place, I think, that guarantee that the next time we scan, we're going to see that that CPU is non-idle. Or if it's gone idle again in the meantime, that the idle time is very short. Yes?
Is a race condition possible in the scan between long and full? So, like the second scan?
So between long and short. Going from short to long, you mean?
Well, then still waiting for time. Or is that
Yeah, in that case, yeah, and the answer is yes, either way. I'm not sure which question you're asking. So the question is there a race condition between long and short?
no, from long to full.
For long to full. Okay, is a race condition from long to full? And the answer is yes, there is. We could scan and say, oh, everybody's in idle, but even before we got done with the scan, okay, somebody could have said, oh, I'm non-idle, the state is long, therefore I'm going to put it back to the not. We could get through and say, hey, everybody's idle and been idle long enough, because we looked at them before they went non-idle. At that point, we do a compare and swap, and we say, okay, if the old value is long, make it be full. But that will fail because the state is now not, okay? So yes, that race can happen, and we have to handle it right. Other questions? Hearing none, let's see, yeah, we got that. If you were at my talk yesterday, a reasonable question to ask would be, this sounds complex, did you mechanically verify this? And the answer, if you were at the end of the talk, is, well, I tried. And we got a bug report in, and they've been responsive. We'll see what happens. And if I don't get, at some point I'll need to use, in any case, even if they get that fixed, I can't really trust that particular mechanism because it's very new and probably has bugs. So in any case, I probably need to fall back on Promel and Spin at some point and get that going. And of course, we've also had reviews, stress tests, and you saw an informal proof of correctness. But those of you who know Murphy, have known him anywhere near as long as I have, there are bugs there somewhere. It's just a matter of finding them. And I'm not going to go through detail this, but the slides will be up later. And here are some things you can look at to get more information on this, some articles from LWN and a few other things. This is kind of a configuration cheat sheet. It's subject to change. This is not exactly the easiest thing to use at this point. For its intended audience, initially, that's not a problem. The real-time guys and the HPC guys have to do a lot of work and configuration to make things work at all. So this isn't a big deal. But over time, we'll probably need to make this easier to deal with. But you need to do config no hertz full y equal y. You'll also probably want to do RCU offload. In fact, I think Frederick has things set up so if you do no hertz y, it does a select on the offload movement. And the reason for that, of course, is that if you leave the callbacks there, you're having two tasks and defeating the whole purpose. You'll need to do a whole bunch of work to move the interrupts around. You'll also want to prevent K-threads from messing you up. And Christoph Lammeter has done a talk a couple times on, they've actually made that work, and it's a fair amount of work, and they've gone through that. I think he did it at End User Summit and at Plumbers. We have some documentation on getting rid of the per CPU K-threads, and there's also some patches. Christoph has a VMstat. The VMstat daemon is kind of obnoxious. It runs every so often, no matter whether you need it or not. What it's doing mostly is just gathering statistics. And if you've never been in the kernel for that duration, there's nothing to gather, all right? And so what you'd like the thing to do is you'd like it just to shut up and go away unless there's been kernel activity. And there's some debate about how that should be done. Christoph has a patch. We've tested it within IBM, and it seems to do what it's supposed to. But more testing, of course, is needed. Anyway, most of this is in 3.10, 3.12, and going in later, and there'll be enhancements going forward. So kind of a summary. Traditionally, there's been a choice between whether you have a general purpose OS or bare metal performance. And what we're trying to do here, there's still more work to do, but I think we've got some good things on us to have both and be able to get very close to bare metal performance while still having the whole OS there if you ever need it. And there are some restrictions. You have to reserve CPUs for housekeeping. Currently in mainline, there is a 1 Hertz residual tick. We leave it there because we aren't sure we've actually covered all of the uses of the scheduling clock tick. It has the same kind of property that BKL did. In fact, RCU used it because it was there, and there's a lot of other people who used it because it was there. This thing just happens every jiffy on every CPU. It's really convenient, right? There is a patch from Kevin Hillman that allows you to turn that off. And if you're experimenting with it and wanting to do stuff with it, you'll need that patch. We haven't put that in mainline yet. We probably ought to make it. It's not just a matter of patching it. You have to give a boot parameter to shut it off. The adaptive ticks and the offloaded CPUs have to be specified at boot time. You can't change the runtime. That seems to be okay at the moment. In the case of the RCU offloading, I think it'll be okay forever because it seems to be okay to offload the callbacks. So if you're uncertain, just offload them all the time anyway and don't worry about it. If it turns out there is some problem, we'll take a look at it, but for right now, just unconditionally offload them and be happy. And then you have the restriction that you have to maintain only 1 runnable task per CPU. That's the challenging part, especially given the K-threads and other things that can show up. And of course, there is still some non-bare metal sorts of things. This will not quite get you to where you could be if you ran just really on the bare metal without an OS. We still have global TLB flush IPIs. In other words, when you're doing this, don't unload some modules, okay? Because if you do that, it'll send global TLB flush IPIs to everybody and cause you trouble. You still have cache misses, and those can happen for any number of reasons. And you still have an MMU, which means you can still have TLB misses and other sorts of things as well. But if you don't have TLB misses and don't have an MMU, your programming life is much harder. You can corrupt anything by messing things around. So I think it's a reasonable trade-off, and you can, if you really are serious, run real bare metal without the operating system if you want to. We aren't preventing you from doing that. And with this work, hopefully with a little bit more integration, we'll be able to maintain energy efficiency as well. So what we've hopefully are doing here is helping Linux go a little bit further into extreme computing. And hopefully that'll be helpful. And of course, the usual slide sponsored by IBM Legal. And we've got a little bit of time left over for questions if we have some more. Yes?
Fixing the 1 runnable task case is nice, but 3% seems like a surprising amount of overhead.
The 3% was for a 100 microsecond timer. Did you check that? It's 10,000 hertz.
No. No. It was no. It's the hertz. The hertz was, I think, 250. What the 100 microseconds was the iteration time in the application.
It's the barrier sequence.
So in other words, you do computation for 100 microseconds, and then do a barrier wait for everybody to get done with that one, and then do another 100 microseconds.
Your slide implied otherwise.
How's that?
Your slide kind of implied.
Oh, okay. No. That would be. We'd probably get a lot more benefit if we ran the hertz at 10,000 hertz. Maybe I'll do that next time. But yeah, it's what happens, the reason that matters is because if you, during one of those 100 microseconds iterations, if you delay any CPU, you delay them all because they have to wait for the slowest guy to get done. And so it kind of amplifies the overhead of the tick.
So deliberate test case, not necessarily a plausible.
No, there really are applications that do that.
It was less than 8
Yeah, yeah, there is.
I'm not saying unreasonable pathological test case.
Well, one guy's pathology is another one's workaday workload, so. But no, this is a very real thing. There really are applications where you have very short iterations and where it's heavily computational.
We have time for one more question.
That one hertz tick that you took off the housekeeping, have you got some way to roll what some extra housekeeping is going on there so you can fix them?
Well, the thing is that it'll just do anything. I mean, so what we do I guess the question was how do we tell what that 1 hertz is doing for us? So what we do for diagnostics is we use ftrace, and we use a ftrace, and we enable the function graph tracer, and then we look at maybe the top couple levels of the function call tree, and then that usually gives us enough information to figure out what bad thing happened. If we enable the 1 hertz tick, we can't really tell. Well, that's just sort of a thing to keep people that run it from messing themselves up. And if you're doing HPC, 1 hertz is probably down in the noise and you don't care. For real time, it's still just as bad as not having it. So the right thing to do there is to apply Kevin Hillman's patch to allow you to disable the 1 hertz tick, and then see what fails, and then yell at us and get us to fix it.
So effectively, it sounds like you're using it as a watchdog.
Yeah, we're using it as we're pretty sure we've got everything, but we aren't 100% sure we've got everything, so, allow it to, and for the HPC guys, that's probably the right answer. I don't know they know this difference. For the real-time guys, it's a real problem, and so they're the ones probably most motivated to apply that patch and find out what's going on. Okay.
Thank you again.
Thank you.